Welcome to the lecture 29 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this lecture, we will focus on carrier velocity saturation first and then mobility model for amorphous material. In last lecture, we have discussed different types of scattering and the mobility models proposed by different scientists for bulk semiconductor mainly. But in last lecture, we have not discussed the effect of carrier velocity saturation. In this lecture, we will cover first the effect of carrier velocity saturation, and including this carrier velocity saturation effect, how the equation for mobility is changed, that will be discussed. Afterwards, we will discuss the mobility models for amorphous materials, because due to presence of huge number of disorders, more disorders in a amorphous material compared to that in crystalline material, scattering will be more, and also different types of scatterings are present. To model these scattering effects and then to model the equation for mobility, different equations have been proposed. So the well-established models for amorphous material will be discussed in this lecture. Velocity saturation. If we consider the basic equation of mobility and relation of this mobility with the average drift velocity, the average drift velocity is mu times electric field. So in last class we have started from the definition of this mobility. We have shown that how average drift velocity is changing with the electric field. Basically, it should vary linearly, and we discussed in last class the mobility model, particularly in the low electric field region. But if we observe the drift velocity at high electric field, it is not maintaining that relationship of linearity, that is V drift velocity is equal to mu times electric field. So for high field behavior, the scattering and other things will be different, and the mean drift velocity or the average drift velocity no longer increases linearly at a high electric field. At the low electric field, it linearly increases because the basic formula for mobility and velocity is like that. So V drift is equal to mu times electric field, mu 0 if we mention. So it should give you linear variation. This is electric field and this is Vd. If you plot, it should give you a linear plot crossing origin. But at high electric field is not happening, it is observed. The impurity scattering is relatively insignificant for high energy carriers. High energy carriers means at a high electric field. If you apply a high electric field between two terminals of a semiconductor material, so carriers will have a drift motion and the carriers will have a high energy due to the external application of electric field. and these energetic carriers in periodic scattering is becoming insignificant, relatively insignificant. So if we plot here the velocity versus electric field, it looks like this. It should go like this. That means up to certain electric field value, it maintains the linear relationship. It follows the linear relationship. But after this particular value, it gradually changes and ultimately it saturates. Not decreases here. You can say this is saturated. How can we model this value, model this effect? Because if you see the equations we have discussed in last class, say basic model or some advanced model, in that case, if you plot the drift velocity as a function of electric field, it would be increasing at higher field also. But practically, for silicon, if it is observed, there is a velocity saturation of carriers after certain electric field. How can it be modeled? This velocity saturation effect can be included in the mobility equation by this formula. Say effective mobility, mu effective, is modified by a term, this term, where this is mu 0 multiplied by this modification term. This is again analytical equation. Mu 0, that the model mobility, low field mobility, that is nothing but already discussed in last class, that is mu 0 is equal to some constant mu 1 plus mu 2 by 1 plus nt by n critical to the power alpha. Alpha is a constant or fitting parameter. Values of mu 1 and mu 2 for silicon we have shown in a tabular form. We have discussed this. And nt is the impurity concentration and the critical impurity concentration. All these values are tabulated and discussed in last class. But actually, the equation should be like that, mu 0 into some factor. In this factor, this is 1 plus electric field E divided by V saturation by mu 0 to the power beta whole to the power 1 by beta. Where beta is nothing but a constant. Again, this is fitting parameter. Beta value is equal to 2 for electron. Generally, it is taken this value. For silicon, it is taken in this way and is equal to 1 for holes. In this equation, why in this form? You observe here at a very high electric field, This is the term. So if you put here the dimension, that is V saturation or V value, this is nothing but mu times into electric field. So mu dimensionally cancelled out. So this will be an electric field. So electric field by electric field. So basically this is factor 1, some unit less, and this to the power factor, and 1 plus that whole to the power minus 1 by beta. At very low electric field, this will be matching with the mu 0 almost. And very high electric field, the factor will be different. The slope of the curve gradually changes. In this region from here to here, so this is linear. After that, this slope gradually decreases and ultimately it saturates. So this saturation velocity is nothing but this velocity. This is called V saturation. That means if you increase the energy electric field, that is if you have a high energy carrier, velocity will no more increases due to more and more lattice scattering. So initially it increases, but beyond that it will not increases. And the formula for V saturation is defined as 3 kT by m star. M star is the effective mass of the carrier. So it's proportional to the T, temperature. If temperature T increases, saturation velocity also will increase. That means it will saturate at a higher value. So the factor, it is coming from this is multiplied with the mu 0 value, the low field mobility. And this model is the beta value on beta, these are chosen in such a way that if E is low, below the critical field EC, mu f will be almost equal to mu 0. If E less than E critical, mu effective will be almost equal to mu 0. Otherwise, it will be low by factor, multiplying a factor. So this is the effect of velocity saturation. Another empirical formula for velocity saturation also proposed by some scientists. This is like this, is 2.4 10 to the power 7. This for silicon. Be careful, this for silicon. And TL, this is a lattice temperature. You have to put this equation TL in equation, that is in Kelvin. So 1 by 1, this by 1 plus 0.8 exponential TL by 600. So if you increase the lattice temperature, it will be more in the denominator, that will be saturation velocity will be less. So it depends on lattice temperature also. This empirical relation can be used to determine the value of saturation velocity in case of silicon. So now we move to the mobility model for amorphous materials, because in amorphous materials the disorder is more. Atoms are not at all arrayed at a regular fashion. There is a random distribution of atoms. In that case, the scattering mechanism will be also more dominating. And to model these, several models have been proposed. Let us first compare with the bulk semiconductor. In a bulk semiconductor, modeling of mobility, so that is mainly characterizing the electron mobility and hole mobility as a function of doping and lattice temperature that we have discussed. Doping basically comes into the impurity scattering. And the model, whatever proposed, that characterizes the saturation velocity, just now we discussed, which is nothing but as a function of lattice temperature. Now, transition from low field mobility to saturated region also we have discussed by the equation by adding an extra factor in the mobility model. In amorphous material, say for example amorphous silicon or whatever the thin film materials which are used, zinc oxide or indium gallium zinc oxide, say cadmium telluride, this is also thin film but it is organic or inorganic category. Anyway, so zinc oxide, IgZO, these types of amorphous material, whatever be the amorphous material, the carrier mobility behaves differently than that in crystalline material. And this is mainly due to absence of long range order. Several mobility models, say for example, these are the models are proposed. First of all, multiple trapping and release model, MTR model, multiple trapping and release. Hopping transport model, HTM. Another is percolation theory, effective medium approach, Gaussian disorder model. This basically discuss with the distribution of trap states, and Full-Frankel, that is field dependent mobility. These are the models famous for amorphous material. Let us discuss one by one. So first of all, say multiple trapping and release models. First of all, we have to remember that in case of amorphous material, there are a huge number of trap states and defect states in the forbidden gap, and carriers move through extended states. Extended states means tail states sometime called. Suppose you have a conduction band minima, this is a valence band maxima. But in between also there are several states due to disorder, specific disorder or defects. So these may be the states which is also present near the conduction band edge or near the valence band maxima. So these are extended states. Just like if you remember the density of states function we have drawn, this was for EC and EV, the density of states, this is the energy and this is along this density of states plotted. So from EC to EV there was no density of states, but in case of amorphous material some states are available. So here instead of these you can get this type of states. So these are called tail state or band tail states. This represents the density of states, closely spaced states near the conduction band and near the valence band. So in this case, carriers move through extended states but get temporarily trapped in localized tail states of band gap, and carriers are thermally excited from tap states. Suppose this is the conduction band. Better to write trap state by black color. And these are the some states which are present, tail states or trap states. These are the also energy states where energy or carrier may reside. And this is the conduction band Now carriers from the conduction band, say electron, may captured to this state, and again from this state they may be emitted and they may reach to the conduction band. This process is called the carriers move through the extended states. Or suppose some carriers move from here to trap state, and in localized states they move to another state, and from that they again emitted back to the original state. So all the communication not directly in the conduction band, through some extended states. This trapped in the trap states. So these are localized states because these are the discrete states, closely spaced discrete states, not like a continuum in like a conduction band. So these are called localized states. So here localized carriers means carriers are localized here. The carrier cannot take part in the conduction process. That's why these states are called localized states. When carrier thermally excited from this state go back to the conduction band, in this way they cover the distance. And here the mobility must be affected because movement is different, not like earlier in a bulk. So mu as a function of temperature that can be written is proportional to T to the power minus n, where n depends on the trap distribution. N is a factor or value. It depends on how much trap states are there. So several trap states may be there. Other trap states may also be there. I have not drawn. So this may be the trap state. So this is the EI, the middle of the gap. So trap states, etc. And this model is used for amorphous silicon or some oxide semiconductor, amorphous oxide semiconductor, say zinc oxide, tin oxide, copper oxide. This behaves like a semiconductor material, oxide but semiconductor material. For this model we have to use. That means mu, whatever you obtained, the bulk mobility model, that should be is equal to some constant into T to the power minus 1. That should be added, should be multiplied to get the mobility in amorphous. Next is hopping transport model. Here the carriers hop between localized states. These are the localized states, hop between localized states, and carriers jump via thermally assisted hopping. And typically this follows the variable range hopping laws. This law is called variable range hopping law. Suppose one carrier is trapped from the conduction band to the localized trap state. From this, they may hop to another states. Again, they may hop to these states. So this hopping mechanism, but is hopping mechanism between localized states. And after that, at the other point, they may also again re-emitted and to go back to the conduction band. So this mechanism of flow of carrier is modeled or equation is proposed by this. Say mu, this will be proportional to exponential minus EA by KT, where EA is the activation energy. Exponential minus value. So it depends on minus, and it also inversely proportional to the temperature. And mu exponential minus T0 by T to the power 1 by 4. There is also another formula. These are related to this hopping transport model. The variable model, this variable range hopping, this VRH model is known as VRH model, is a low temperature charge transport. Be careful, at very low temperature also this hopping may occur in a disordered material. Disordered material means particularly amorphous material. And this leads to a characteristic temperature dependence of the conductivity, often described by Mott's VRH law. It is a very common model for VRH, particularly in materials with a relatively constant density of states near the Fermi level. This is very important. This model is generally applied to the material where a constant density of states near the Fermi level is present. And it predicts the temperature dependence of conductivity as sigma, as conductivity, this is proportional to exponential minus T0 by T, because sigma ultimately will be related to the mu. Sigma, how it related to the mu? Sigma is a conductivity. It starts from J is equal to sigma E, sigma into electric field, this the formula, and where sigma is n mu n, because sigma E, or you can write J is equal to N Q V, VD average for N type carrier. If we write a Jn, this indicates Jn drift value, N concentration of carrier electron into Q into mu E. Mu E, V is nothing but mu times E. So J is equal to sigma E, and J is equal to this into E. That means sigma is equal to NQ mu N for N type material. But generally sigma, in case of both carriers are present, is taken as NQ mu N plus P, concentration of holes, Q mu P, concentration of electron, concentration of holes. If both are present in an intrinsic semiconductor, for example, you have to use N and P, Q and mu times mu, the mobility of electrons and holes. But if it is a extrinsically doped, sufficiently extrinsically doped, suppose a N-type material. So if it is a N-type material, so N is very high compared to the P. So in that case, sigma can be written as NQ mu N. And for P-type material, only P-type material, you can write sigma almost equal to PQ mu P. Almost equal to. But actually in N-type material, you should consider the mobility of electron as a majority electron and mobility of hole as a minority hole. So both terms should be present. But actually this is dominating term. So sigma, this conductivity, which is related to the mobility, it is proportional to the exponential minus T0 by T. T0 is a constant, some constant value, and T is the temperature. So this is the mechanism of hopping transport model. Another model, this is called percolation theory, which is also called the effective medium approach. In that case, the carrier transport occurs through a network of favorable paths. Favorable paths means when it looks some path is favorable, maybe hopping, maybe thermionic emission, anyone. So favorable paths in a disordered energy band gap material, it is called percolation. Particularly some oxide materials, we increase the doping, increase the conductivity or increase the carrier concentration by mixing some metals. Say for zinc oxide is a oxide amorphous semiconductor. To increase the carrier concentration, we dope gallium or we dope some type aluminium to make it aluminum doped zinc oxide or gallium doped zinc oxide or IgZO, indium doped zinc oxide. These are the famous materials for solar cells and for ITO layers, for electron transport layer, hole transport layer, etc. So in this type of material, due to presence of some metallic atoms in the oxide semiconductor, the band gap will be like this. There will be some trap states like this. This is the trap state. These are the trap states. And also you can have some barrier in the conduction band due to presence of metal. So this is say metal due to presence of metal atoms. And when carrier comes from or trapped from or captured from a conduction band to a trap state, it may come here. And they may released also due to the thermal energy at temperature, it may reach back to the conduction band. Also some cases, some carrier may overcome the barrier by thermionic emission process. This is thermionic emission process. So maybe it is captured and it is released back to the conduction band, and from that it is thermically emitted across the barriers, and in this way there is a technique to propagate is called the percolation technique. And in that case the barrier, this q into phi barrier, this height of the phi barrier, and d is the barrier width, a gap between two successive barriers, are important parameters which have a role on the mobility. These are there is a critical energy level or called mobility edge above which carriers can move, otherwise your carrier cannot move. This energy level is called the mobility edge. And higher paths with higher connectivity, there is a less resistivity, there is higher connectivity, and energy continuity is dominate the continued this conduction process. Mainly these are influenced by energy barrier distribution that I have mentioned. How the metals are distributed, or if you increase more and more number of metal in a zinc oxide, say, to increase carrier concentration more, there is more conductive, but it may affect mobility in a reverse way. So more and more barriers will be present in the conduction band, and due to that the motion of carriers will be affected. And this can be modeled by just multiplying two factors. Suppose if you have the numbers, that is density of electron in the conduction band, say NCB, and if the trap density, the carriers in the trap states, that is NT, and if you have the ratio, so that is a factor, so say NCB by, say, factor NCB by NCB plus NT, or you can write trap. These factor, suppose this factor you are calling, there is a trap factor, F trap. NCB and N trap, you know, from the basic equation of this NCB can be written. This NCB we have already discussed. This depends on density of states in conduction band, that is NC exponential. This basic relationship of distribution of the Fermi-Dirac or Boltzmann. This is EF minus EC by KT. And similarly, N trap, this can be written as NT. Suppose T is the density of effective density of states, trap states, and at the position say ET, energy level say ET. So NT, it will be NT KT exponential E F minus EC by KT. This will be N trap is equal to NT KT exponential EF minus EC by KT. This depending on value, this can be derived from this equation. So if you can determine the factor, this factor should be multiplied with the original mobility model for the bulk. Also, due to this emission process, this is hampered, I told you. So this emission process, this can be also modeled by another factor. If you see, this is suppose percolation, PERCOL, this factor due to percolation. A factor due to percolation you have to calculate. This fraction can be written as, with increasing the barrier height it decreases. So exponential minus Q times phi barrier in volt. So Q times means this gives you energy by KT. So in this way you can model or you can change. So mu in amorphous, in this model, mu in say amorphous silicon, it will be mu effective, which is already discussed, multiplied by this factor F trap. This factor actually I am taking F trap, yes, F trap into F of percolation. Simply in this way also you can model. And due to presence of these factor values less than 1, much less than 1, effective mobility will be reduced drastically in case of amorphous silicon or other metal doped oxide semiconductor material. Say GaZO, that is, or GZO, gallium doped zinc oxide, AZO, that is aluminium doped zinc oxide, or say IGZO, indium gallium zinc oxide, IGZO. These are the materials where you can apply this model. Mainly presence of barrier is determined by this. Also distribution of barrier is important in this case. So next model is Gaussian disorder model. Actually here Gaussian disorder model is not a separate model for mobility, but is a distribution of the trap states, whatever the localized states that have energies distributed in a Gaussian density of states. If you use the distribution of that energy in a Gaussian as a Gaussian density of states, and if you apply these states for the models discussed earlier in last 2-3 models, that will be the Gaussian disorder model. So hopping occurs between sites with Gaussian distributed energies. So hopping also will occurs based on these states. So in the hopping model you have to use the distribution of energy states. There is a Gaussian distribution, not a constant distribution or uniform distribution. Also this strongly field and temperature dependent, and mobility decreases with increasing disorder. This is quite obvious for all these things. This model is basically mainly used for organic semiconductors, that is organic solar cell. And this Poole-Frankel, there is a field dependent mobility. Here also the pull dependent term is modified, and the current flow, that is J, is equal to some constant exponential minus phi minus beta pf. These are the also factor, that is empirical or fitting parameter, root over E by kt into E. So this part actually represents the conductivity part, sigma E, just like this. So this is determined by a factor phi. Phi, that is, there is the barrier height. You see, phi is the zero field barrier height, minus beta pf. This is pull Frankel coefficient, multiple time root over E divided by kt. So this total energy, but this phi is in here, will be in electron volt, and T is the temperature. So often used for, that is GDM model that we have discussed earlier, that is a Gaussian disorder model. In Gaussian disorder model, after considering the states are distributed Gaussian, so J, this formula can be used. K is constant here, not Boltzmann constant, is a different constant. Be careful. And E is the electric field. So these are the model we have discussed here for amorphous material, and it is always seen that mobility in case of amorphous material is much less than mobility in a bulk semiconductor. Several disorders are present, as we have discussed, and we have also discussed the hopping of carriers through trapped states, multiple hopping plus percolation, all these things, they may be combined also. And to calculate this model, to determine the mobility models or mobility for these amorphous type materials, we have to consider the distribution of trap states. And distribution of trap states or tail states, if we consider Gaussian distribution, then Gaussian distribution model will be there, and that is used for mainly organic semiconductors. Another important thing that we have discussed and we have shown, in case of metal doped amorphous oxide materials, say for example gallium doped zinc oxide or aluminum doped zinc oxide material, due to presence of barrier in the conduction band, barrier due to metal atoms. So to overcome this barrier, thermionic emission model is considered, and to include this model with the multiple hopping or trap assisted hopping mechanism. So both types of mechanism may be combined in such a material of, that is IGZO, GZO, AZO, etc. And for that we can use that models. We have also discussed the carrier velocity saturation. At high electric field, we have shown in case of bulk semiconductor, velocity is not increasing linearly with electric field, but in case of low electric field, this linear relationship is maintained. And at high electric field, due to high energy carriers, more scattering are there. So due to this more and more scattering, velocity will not further increase, it tries to saturate. So more scattering of high energy carriers is responsible behind this saturation. And for silicon, it is saturation velocity, it is observed, and saturation velocity can be also modeled by formula, that is root over 3 kt by m star. For silicon, it is the value in the range of say 10 to the power 5 centimeter per second, 10 to the power 5 meter per second, or 10 to the power 7 centimeter per second. However, in case of gallium arsenide material, between low mobility, linear variation and saturation region, there is a overshoot region. So velocity of drift velocity overshoots in case of gallium arsenide, that I forgot to mention. This will be like this. This is the saturation velocity, Vd, This is electric field. This is for gallium arsenide. So this overshoot that is of the velocity is a special characteristics or mechanism here. Up to this region, this is remaining. So model for this gallium arsenide, we have to consider the region, linear region, then some decrement region, and then some saturation. So combination of three portions and three different equations, the model for mobility of gallium arsenide can be derived. So these are the references for this lecture. Thank you.